In 1969, two men landed on the moon. The whole world knows that. But there is something almost nobody knows, that they almost never came back. Not because a rocket failed, not because a computer crashed, not because of a space storm or an asteroid or anything that sounds dramatic, but because of a backpack. Buzz Aldrin was removing his backpack in the cramped cabin. The backpack brushed against the instrument panel. A small snap, and a piece of plastic the size of a fingertip fell to the floor. That's all. But that piece of plastic was the switch that armed the only engine capable of lifting them off the moon. Without it, they couldn't take off. No rescue ship, no plan B. And the people in Houston were 384,000 kilometers away. No one could come pick it up for them. That night, while the whole world celebrated, two men lay in the dark on the moon, staring at that piece of plastic on the floor, not knowing if they would ever see Earth again. As always, I'd love to know where in the world you're listening from and what time it is where you are right now. Don't forget to subscribe to Space Lull so you never miss what's coming next. And now, let's begin. July 21st, 1969. Around 1 a.m. Houston time. Eagle, the name of the lunar landing craft, had touched down on the flat plain called the Sea of Tranquility more than 21 hours ago. The historic moonwalk was long over. Armstrong and Aldrin had come back inside. They had removed their heavy spacesuits, and now they were preparing to do something that sounds remarkably ordinary. Try to sleep a little before liftoff. But first, Buzz Aldrin needed to take off his backpack. Not an ordinary backpack. This was the PLSS, the Portable Life Support System, a rigid rectangular unit weighing around 54 pounds, locked onto the back of his spacesuit. Inside, oxygen, a cooling system, batteries, and a radio. Everything that kept an astronaut alive during a moonwalk. Without it, stepping outside meant instant death. But they were inside now. The backpack had to come off. The Eagle's cabin was very small. How small? Imagine a standing wardrobe, the ordinary kind you'd find in a bedroom. Now put two full-grown men inside it. Two men wearing thick, rigid spacesuits with tubes and cables running all over them. That was Eagle's ascent stage cabin. 235 cubic feet. No seats, they stood, held in place by thin restraint cables attached to the floor. The instrument panel covered the entire front wall with hundreds of switches, buttons and gauges, all within elbow's reach. In that space, Aldrin began removing his backpack. He turned. The backpack brushed against the instrument panel. A small snap. Aldrin looked down. On the cabin floor, dusted with fine grey lunar powder they had accidentally tracked in from their boots and suits, lay a small black piece of plastic, no larger than a thumbnail. He knew immediately what it was. Along the front instrument panel ran a row of circuit breakers, small round switches used to open and close electrical circuits throughout the ship. Each had a small plastic head that an astronaut could push in or pull out with a finger, even through thick gloves. And that plastic head was exactly what Aldrin was looking at on the floor. Its number? Circuit breaker 16. Its label? Engine arm. To understand why this mattered, think of it this way. You have a car. You want to start the engine. You need the key. No key, the car won't start, even if the engine is perfectly fine, even if the tank is full, even if everything else is working perfectly. The engine arm circuit breaker was that key. When an astronaut pushed it in, it closed the electrical circuit, sending a signal to the ascent engine's ignition system. Without that signal, no matter how many times you press the start button, the engine would not respond. And the ascent engine, that was the only thing that could lift Eagle off the moon. Not the descent engine, that had already been used for landing and would stay on the surface forever. Not Columbia's engine, the command module waiting in orbit 60 miles above, with no ability to come down and pick them up. Just one engine, one chance, and the switch that armed it was now lying on the floor. Aldrin reported to Houston. His voice was calm, not because he didn't understand what had just happened, but because that was what they were trained for. NASA's test pilot astronauts of that generation Most were former military pilots, used to flying aircraft that could kill them at any moment. They learned that panic doesn't solve problems, it only makes everything worse. So Aldrin reported, Houston acknowledged, and the two astronauts were asked to do something that sounds nearly impossible, given the circumstances. Try to get some sleep. Liftoff was scheduled for 5:54 p.m. the following day, Houston time, still more than 15 hours away, and the two men had been awake for nearly 20 consecutive hours, from before landing, through the historic moonwalk, to now. An exhausted astronaut could make mistakes during liftoff, and in space, mistakes don't come with second chances. Houston needed them to rest. Houston would stay awake. And so, that night on the moon, one of the strangest scenes in the history of space exploration unfolded quietly. Two men who had just walked on the moon, who had just done what humanity had dreamed of for thousands of years, were lying in the dark, on the floor and on an engine cover of a metal box, trying to close their eyes. And beneath them, in the lunar dust, a small black piece of plastic lay still, waiting. But to understand why that piece of plastic held such power over life and death, you need to know how the machine they were sitting inside had been built. Because Eagle was no ordinary spacecraft. It was one of the strangest, most audacious machines human beings had ever constructed, and everything about it, every design decision, every trade-off, had led to this night. To understand why a piece of plastic the size of a thumbnail could end two lives, you need to understand how Eagle was built, and the answer will surprise you. Because Eagle wasn't built to be beautiful, wasn't built to be comfortable, wasn't built to fly for long. It was built to do exactly one thing, and only one thing: land on the moon, then fly back up. After that, it could disappear. And it did. Eagle was essentially two different spacecraft bolted together. The bottom half, called the descent stage, was the legs. It had the large engine to slow their approach to the moon, 4 landing legs with rounded footpads like spider feet, and equipment bays holding scientific instruments, batteries, and fuel. It was the first thing to touch the surface. It absorbed the impact. It kept everything stable. And when Armstrong and Aldrin left, it stayed behind. Forever. Eagle's descent stage is still standing at the Sea of Tranquility to this day. No one has gone to retrieve it. No one has plans to. It will remain there for billions of years. Because on the moon, there is no wind, no rain, nothing to wear it away. A spacecraft designed to be left behind, from the very beginning. The top half, called the ascent stage, was what mattered most. This was the living quarters. This was where Armstrong and Aldrin stood, ate, reported to Houston, tried to sleep. This was where the instrument panel, guidance computer, radio, and life support systems lived. And most importantly, this was where the ascent engine sat. The engine that would lift them off the moon. The ascent stage was the lifeboat. But unlike any lifeboat you've ever seen, no large windows, no seats, no room to stretch your legs. Just 2 small triangular windows, each barely wide enough to look through with one eye, and a hatch at the front for astronauts to crawl out during moonwalks. And the entire exterior was wrapped in a thin gold insulating blanket, material so thin it looked like someone had taken gift wrap and taped it onto a spacecraft. It didn't look like a spacecraft at all. It looked like a tin box, hastily wrapped. But that was exactly what its designers intended. The company that built Eagle was Grumman, an aircraft manufacturer based in Bethpage, New York. And when NASA contracted them to design the lunar landing craft in the early 1960s, Grumman understood one crucial thing immediately. In space, everything you add has a price. Not a price in money, a price in mass. Every pound added to the lander meant the Saturn V rocket had to carry more fuel to push it into orbit. More fuel meant a heavier rocket. A heavier rocket meant even more fuel. This was a loop with no end. Engineers called it the tyranny of the rocket equation. So Grumman did something that few engineers dare to do. They removed everything that wasn't absolutely necessary. No seats. Astronauts stood, far lighter than cushioned chairs. No large windows. Small frames, just enough to see out during landing and liftoff. No complex air conditioning, only the bare minimum to keep temperatures within survivable limits. And the outer hull, instead of thick steel, Grumman used aluminium alloy so thin that in some places it was only 0.012 inches thick, thinner than a sheet of ordinary paper 3 times over. If an astronaut accidentally jabbed a pen into exactly the right spot, they could puncture the hull. This was the most fragile, lightest, most audacious spacecraft humans had ever built at that point in history. But there was one thing Grumman never compromised on: the ascent engine. Because the ascent engine had no second chance. If the descent engine failed during landing, the crew could abort, fire the ascent engine and escape. But if the ascent engine failed during liftoff, there was nothing to abort to, no plan B, no backup engine, just the lunar surface and a few hours of oxygen left. So everything else could be cut, but not that engine. And to ensure it would never fail, the engineers arrived at a decision that sounds completely counterintuitive. They made it as simple as possible. Not complex, not multiple backups, not the most advanced technology available. Simple, almost primitive. And that is the story of the next part. The story of the small, strange, almost impossibly reliable engine that the entire Apollo 11 mission placed its bet on. Spring 1963. Bell Aerosystems, an aerospace company in Buffalo, New York, received a contract from NASA. The task? Design the engine for the ascent stage of the lunar landing craft. Grumman's requirement came in a single sentence. One sentence only, but it shaped every design decision over the next 6 years. High reliability through simplicity. Not the most advanced technology, not the highest performance, not the smallest or lightest. Just one thing: never fail. And to achieve that, Bell Aerosystems began a process engineers called stripping away. They looked at every component of the engine, every mechanism, every system, and asked one simple question: can this fail? If yes, remove it. Find another way without it. The first thing eliminated: the turbopump. In most rocket engines, the turbopump is the heart of the fuel delivery system. It pumps fuel and oxidizer from the tanks into the combustion chamber at extreme pressure. Without it, fuel can't enter the chamber and the engine can't run. But turbopumps have a problem. They have rotating parts, turbines, gears, shafts spinning at tens of thousands of revolutions per minute. Anything that spins fast can fail. Bearings wear out, turbine blades crack, shafts go off-center. Bell Aerosystems decided no turbopump. Instead, they used a pressure-fed system, a far simpler approach. Helium gas compressed at high pressure was used to push fuel from the tanks into the combustion chamber. No rotating parts, no turbines, no gears, just pressure pushing liquid through a pipe, like squeezing a plastic bottle to make water come out. Simpler, fewer things that could fail. The second thing eliminated: the throttle. Most rocket engines can adjust their thrust, increasing when acceleration is needed, decreasing for control. Eagle's descent engine had a throttle, so the crew could control landing speed. But a throttle means flow control valves, and valves can stick, can leak, can fail in the wrong position. The ascent engine had no throttle. It had only 2 states: on or off, full thrust or nothing. When you started it, it delivered all 3,500 pounds of thrust immediately. No more, no less. No way to adjust. This meant the astronauts could not control their takeoff speed. They could only fire it and hold on until orbital velocity was reached. Less control, but fewer things that could fail. The third thing eliminated: the gimbal. On most rockets, the engine can swivel slightly left or right to steer, called gimbaling. This is how the Saturn V steered itself when launching from Earth. But a gimbal means the engine is mounted on a movable joint, and joints can seize, can crack, can swivel the wrong way at the worst possible moment. The ascent engine had no gimbal. It was mounted fixed, pointing straight up, unable to swivel. To steer during flight, Eagle used 16 small thrusters mounted at different points on the hull, each firing a small jet of gas to rotate the craft in whatever direction was needed. More complex to navigate, but the main engine simpler. And finally, the most important element kept and protected more carefully than anything else: the fuel. The ascent engine burned a mixture of two liquids, aerosine 50 and nitrogen tetroxide. These two substances share a strange property that chemists call hypergolic. When they touch each other, they ignite instantly. No spark needed, no ignition system, nothing required to trigger the reaction. Just open the valves, let the two substances meet inside the combustion chamber, and the reaction happens immediately, in an instant. You can imagine it this way: like pouring vinegar into baking soda. The reaction happens right away, nothing else needed. Except with hypergolic fuel, the reaction doesn't create bubbles. It creates flame at thousands of degrees and enough thrust to lift a spacecraft off the surface of the moon. No ignition system meant one less thing that could fail. The result of all that stripping away was an engine that looked almost primitive compared to what technology of that era could produce. One combustion chamber, one nozzle, two valves, one for each propellant, and a pressure system to push the fuel in. No turbines, no gears, no gimbal joint, no ignition system, no throttle, and most importantly, no backup for the combustion chamber or nozzle. Every valve, every wire, every sensor had a redundant copy, but the chamber, just one. The nozzle, just one. If either failed, nothing could replace them. This was the decision that Bell Aerosystems engineers lost sleep over for many nights. In the end, their reasoning was simple. The combustion chamber and nozzle are passive components. No moving parts, no friction, no wear points. What causes failures is usually what moves. What stands still is far less likely to fail. And they were right. 6 lunar landings, 6 liftoffs, not one failure. But on that night, July 21st, 1969, no one knew that yet. They only knew that the perfect engine was sitting right below the cabin floor, ready to work, and the only switch that allowed it to receive its start command was lying in the lunar dust beneath them. The engine needed no spark. The engine needed no turbo pump. The engine needed none of the dozens of complex systems that other engines required. But it needed one small electrical signal to know it was authorized to fire, and that signal was blocked by an open circuit, where a small plastic tip had just broken away. Meanwhile, in Houston, dozens of engineers were beginning their work, and the night had only just started. Stop for a moment and think about this. Armstrong and Aldrin had just done what humanity had dreamed of for thousands of years. They had just set foot on another world. They had just walked on the surface of the moon, looked up at Earth hanging above them like a giant blue marble in the darkness of space. And now they were trying to sleep, in a metal box, at 61 degrees Fahrenheit, with a broken piece of plastic on the floor. There are no words in any human language to describe that contrast fully. Eagle's ascent cabin at night was not a comfortable place to rest. Even under normal conditions, if anything on the moon could be called normal, this was already one of the worst sleeping environments any human had ever endured. Start with the temperature. Outside Eagle, the lunar surface was experiencing lunar daytime, temperatures out there reaching over 250 degrees Fahrenheit in direct sunlight. But inside the cabin, the cooling system had brought the temperature down to around 61 degrees Fahrenheit. That doesn't sound terribly cold, but remember, Armstrong and Aldrin had just spent hours in heated spacesuits. Their bodies were accustomed to warmth, and now, without those suits, without blankets, with nothing to hold in heat except thin undergarments, 61 degrees felt far colder than the number suggests. And there was another problem. They couldn't turn off the light completely. Light from outside filtered in through the 2 small triangular windows. Earthlight reflected off the lunar surface, bright enough to see everything inside the cabin without needing a lamp. And the way Eagle was parked at Tranquility Base meant the guidance telescope, a small optical scope mounted on the wall, was channeling that light directly into Armstrong's face. Not faint light, enough to make closing his eyes impossible. Armstrong tried lying on the ascent engine cover, the flat metal panel in the middle of the cabin floor, with the engine combustion chamber directly beneath it. He tied a strap from the wall to use as a footrest, because in the moon's low gravity, 1/6 of Earth's, the body has a tendency to drift slightly if not anchored. Lying down without securing yourself meant slowly floating upward and bumping into a wall. Aldrin chose the floor, curling up in the small space beneath the instrument panel, knees pulled up toward his chest. 2 men, 1 box, and an entire night ahead. They couldn't sleep. Later, in post-flight debriefings, both Armstrong and Aldrin admitted this. Not because they were overwhelmed with worry, or at least that's what they said, but because everything in that environment worked against sleep. The noise from the life support system, pumps, valves, cooling fans, created a continuous background hum, not loud, but never stopping. The light coming in with no way to block it, the temperature just cold enough to keep the body from fully relaxing, and the sleeping position, lying on a hard metal surface or curled up on the floor, not something the human body easily accepts after 20 consecutive hours of activity. But there was something else. Something neither man mentioned in official reports, but something you don't need them to say out loud to understand. Beneath the floor, in the lunar dust, the small black piece of plastic was still there. Meanwhile, in Houston, Mission Control was completely awake. Electrical engineers were working with Eagle's circuit diagrams, large sheets of paper covered in electronic symbols, connecting lines, switches, relays, circuit breakers, and branch points. They were tracing every electrical path through the system, looking for any alternate way to send the ARM signal to the engine without using that broken circuit breaker. The problem wasn't as simple as it looked. A circuit breaker isn't just an on-off switch. It also protects the electrical circuit. If a fault occurs anywhere in the system, the circuit breaker automatically trips to prevent excess current from destroying more critical components. That's why Aldrin didn't want to use a metal object to close the circuit. If he bridged the 2 contact points with metal in the wrong way, he could create a faulty electrical connection, not closing the ARM circuit, but shorting out part of the ship's electrical system, replacing a solvable problem with an unsolvable disaster. The engineers in Houston found a partial workaround through an auxiliary wire in the system that could in theory route the ARM signal along a different path, bypassing the broken breaker entirely. But no one was fully confident it would work. This was a theoretical option, never tested in real conditions. No one had ever imagined they would need it. In aerospace engineering, untested is the most frightening word there is. About 10 hours passed that way. Armstrong and Aldrin took turns dozing for a few broken hours. Not enough to call sleep, but enough that their bodies didn't completely give out. Houston continued its analysis. And the moon, entirely indifferent to everything happening inside the small metal box parked on its surface, remained as silent as it had been for the past 4.5 billion years. Outside Eagle, Tranquility Base lay still in partial shadow and earthlight. The footprints from the moonwalk remained undisturbed in the dust, and would remain so for tens of millions of years. The American flag stood planted in the soil, its horizontal crossbar jammed before fully extending, making it look like it was waving in a wind that didn't exist. And 384,000 kilometers away, on Earth, the world was still celebrating. No one knew that in a desk drawer somewhere in the White House, there was a piece of paper waiting, a speech, already written, for a scenario no one wanted to happen. Mission Control, Houston, Texas. A large rectangular room, low ceiling, white fluorescent lighting. Dozens of consoles arranged in rows, each one a screen, a headset, and a thick stack of documents. At the front of the room, a massive display showed orbital trajectories, technical readouts, and Eagle's position on the lunar surface. The night of July 20th into July 21st, 1969, no one in that room was sleeping. Each person seated in that room had a title. Flight Director, FIDO. Flight Dynamics Officer, GUIDO. Guidance Officer, EECOM. Electrical, Environmental and Consumables Manager. Each title owned one specific system on the ship, tracking hundreds of technical parameters in real time. That night, the most important person in the room was the engineer responsible for Eagle's electrical systems. His task was to answer one question. Was there any way to start the ascent engine without the engine arm circuit breaker? To answer it, he had to do something that sounds simple but was extraordinarily complex. Read through the entire electrical schematic of Eagle from beginning to end, in the middle of a Houston night, knowing that 2 men on the moon were waiting for the answer. Eagle's electrical schematic was not 1 page, not 10. It was hundreds of pages of technical documentation, each page covered in electronic symbols, connecting lines, switches, relays, circuit breakers, and branch points. Every system on the ship, life support, guidance, communications, propulsion, had its own circuit, and all of them were interwoven in ways that only the people who designed them fully understood. Those people were in Bethpage, New York, Grumman's offices, and that night they weren't sleeping either. Houston called Grumman, Grumman called Bell Aerosystems. Engineers from 3 different locations across America, Houston, Bethpage, Buffalo, began working together over the phone, each holding a set of electrical schematics, tracing every wire together. And they found this. Within Eagle's electrical system, certain circuits had been designed with alternate paths, a secondary route that current could take if the primary route was blocked. This was standard design practice in aerospace engineering, because in space, you can't call a repair crew. The electrical engineers discovered that the ARM signal could, in theory, be routed to the engine through a secondary wire, bypassing the broken breaker entirely. That sounded like good news, but there was a problem. That secondary wire was not designed to carry continuous electrical load throughout a liftoff. It was designed as a temporary signal channel, enough to check system status, not enough to sustain an engine start command through 435 seconds of burn. In theory, it could work. In theory, the current was small enough not to cause an overload. But no one had tried it. No one had tested it under real conditions, and no one in that room could say with absolute certainty that it wouldn't cause some other problem during liftoff. In aerospace engineering, might work and will work are very different things. But this wasn't the first time Mission Control had faced a problem with no clear answer. Think back to July 20th, less than 24 hours earlier, when Eagle was descending and the guidance computer suddenly displayed alarm code 1202, an error code that even the astronauts didn't recognize. Armstrong read it aloud over the radio. The room in Houston went quiet for a few seconds. Then a young voice, Jack Garman, 24 years old, software engineer, said, "Go, we're go on that." Error 1202 was a memory overload warning. The computer was trying to process too many tasks at once, but it was programmed to automatically prioritize the most critical ones and drop the rest. It could continue functioning. Garman knew this because he had personally studied and memorized every possible error code. Not because anyone asked him to, but because he thought he might need to know. History turns on moments like that. One person, one piece of information, 1 second of decision. That night, Mission Control was looking for another Jack Garman, someone with the right answer at the right moment. But the answer they found was imperfect. The secondary wire might work, but no one could be certain. And if it didn't work, no other clearly defined option had been identified. The truth was, that night in Houston, no one could sleep. Not because they were working continuously, but because at the bottom of every analysis, every calculation, every cross-country phone call through the night, there remained a gap that no number could fill. That gap had a name, unknown. And while Houston wrestled with that gap, in Washington, D.C., inside the White House, a man was sitting before a blank page. His name was William Safire. He was a speechwriter for President Nixon, and that night he was not writing a victory address. He was writing something else. July 18th, 1969, 2 days before Eagle landed, 3 days before the night of the broken switch. Apollo 11 was on its way to the moon, 2 days out from Earth, crossing the empty space between two worlds. Nothing to see through the windows but absolute darkness and stars that never twinkled. In Washington, D.C., inside a White House office, William Safire sat down before a blank page. Safire was a speechwriter, one of the finest of his generation. His job was to find language for the great moments of history, the words a president would read before cameras, before the nation, before the world, in the moments when no one knows what to say. And that day, his boss, H.R. Haldeman, White House Chief of Staff, had given him a special assignment. Write a speech for the case that Armstrong and Aldrin don't make it back. Sapphire wasn't the first person to think about this. The tradition of preparing for failure in great missions has a long history. Before the Normandy landings on June 6, 1944, D-Day, General Dwight Eisenhower had handwritten a short note ready to be read to the public if the invasion failed. In it, he took full responsibility upon himself, blaming no one. That note was never used. Eisenhower kept it in his jacket pocket throughout the day, then discarded it after news from the beaches began to turn hopeful. Sapphire knew that story, and he knew this was the moment to do the same. He also thought of Rupert Brooke, the English poet who died young in World War I, who had written poems about sacrifice and the beauty of dying for something larger than oneself. Sapphire wanted his speech to carry that spirit, not tragedy, but solemnity, not despair, but acceptance. He began to write. The draft he completed that day carried a simple title, In Event of Moon Disaster. It began with this sentence, and read it slowly because every word was chosen with great care. Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace. One sentence, two symmetrical halves, and in the distance between explore and rest, the entire story of Apollo 11 compressed into 15 words. The speech continued. Sapphire wrote about what Armstrong and Aldrin represented, not just for America, but for all of humanity. He wrote that they knew there was danger and chose to go anyway, that their sacrifice was not failure, but part of a longer journey humanity was taking, step by step, out of its cradle. And then he wrote the instructions, not part of the speech itself, instructions for Haldeman, for the people who would have to carry out the next steps if the worst happened. Those instructions had 3 steps. Step 1. Before the president read the speech on camera, he would personally call each astronaut's wife. Not through a spokesperson, not through a secretary. Nixon himself would pick up the phone and call each home directly. Janet Armstrong, Joan Aldrin. 2 women sitting in front of their televisions, watching alongside the rest of the world, not knowing the phone was about to ring. Step 2. After the speech was delivered, a clergyman would conduct a memorial service. Not an ordinary funeral, no coffin, no flowers, nothing to bury. Sapphire recommended using the ritual of burial at sea, the naval ceremony for soldiers lost at sea whose bodies cannot be brought home, because Armstrong and Aldrin would be in an environment with no life, because no one could come to bring them back, and because the ocean and space, in some sense, are both vast regions that humans have dared to enter, and from which they sometimes do not return. Step 3. After the ceremony, NASA would cut communications with Eagle, not because equipment had failed, not because the signal was lost, but as a deliberate decision to let the 2 men go in silence. No more voices from Houston, no more system checks, no more, Eagle, this is Houston, over. Just silence, from Earthside, stretching on until the oxygen ran out, until everything ended in a way that no one needed to hear. Sapphire sent the draft to Haldeman on July 18th. Haldeman read it, put it in a drawer, and never showed it to Nixon. Not because he thought the scenario couldn't happen, but because he understood that there are things a president should not read before an event occurs, because reading it in advance means part of the mind has already begun to accept that possibility as real. And Haldeman didn't want Nixon walking into the coming days with the shadow of that speech already in his head. The speech sat in that drawer for 30 years. In 1999, a journalist named Jim Mann was researching documents at the US National Archives when he found it, in an unmarked box of files from the Nixon era, among thousands of other pages. He read it, and understood immediately that he had found something important. The speech was published for the first time, 30 years after it was written. The press called it the greatest speech never delivered. Sapphire, by then a celebrated columnist at the New York Times, confirmed the story and described the circumstances under which he wrote it. And the question many people asked after reading that speech was not, would Nixon have read it well? But, if it had needed to be read, what would have had to happen to lead to that? The answer to that question was exactly what the engineers at NASA feared most. Not one scenario, not two, but three specific scenarios, three different paths leading to the same end, and each one was frightening in its own way. In aerospace engineering, there is a principle called failure mode analysis. Before a mission is approved to fly, engineers must sit down and do something that sounds deeply pessimistic. List every way things could go wrong. Not to frighten people, but because only when you know exactly what can fail, can you design to prevent it. For Eagle's liftoff, engineers had identified three primary failure scenarios. Three scenarios, three different paths, one destination. Scenario 1. The engine doesn't ignite. This is the simplest scenario to picture, and in some sense, the most merciful of the three. Armstrong and Aldrin press the start button. Nothing happens. The engine stays silent. Eagle sits motionless on the surface of the moon. From that moment, their fate is determined by a single number, the amount of oxygen remaining in the ship's life support system. Eagle carried enough oxygen for roughly a few days of surface operations, but most of that had been consumed during the moonwalk and their time on the surface. Estimates suggested that at the time of liftoff, they had around 24 hours of oxygen left if they stayed inside the ship and minimized activity as much as possible. 24 hours, during which nothing could change. No rescue ship. No way for Michael Collins in Colombia to land and pick them up. The command module was not designed to land, and even if it had been, Collins wouldn't have had the fuel to attempt it. Houston would watch the life support readings declining hour by hour, would talk to them, would try to find any option at all, and in the end, would hear their voices grow weaker, then fall silent. This was the scenario Sapphire had written the speech for. Scenario 2. The engine ignites but shuts down early. This scenario is more complex, and in some sense more cruel. The engine fires. Eagle lifts off the surface. The astronauts feel the thrust, see the lunar surface dropping away through the small window. One moment of hope. Then the engine stops. Not because the fuel ran out, but because of a mid-burn technical failure. Perhaps a fuel valve jammed. Perhaps the pressure in the propellant feed system dropped suddenly. Perhaps a line was blocked by propellant residue that had solidified in the extreme temperatures. When the engine cuts out mid-burn, Eagle doesn't have enough velocity to reach orbit. It doesn't fly up. It follows a parabolic arc, climbing briefly before beginning to fall back. In the moon's low gravity, that process happens far more slowly than it would on Earth. The astronauts would have time to watch the lunar surface approaching, slowly, unstoppably. A low-speed impact might not kill them instantly. It might damage the ship. It might injure them. And after that, they would be inside a damaged craft, on the surface of the moon, with less oxygen than before. This was the scenario engineers spent the most hours analysing, because it had too many variables, too many points where things could go wrong, and no way to prepare for all of them. Scenario 3. Loss of control during stage separation. This was the scenario no one wanted to name, the one engineers described in dry technical language to avoid having to picture it too clearly. For Eagle to leave the moon, the ascent stage had to separate from the descent stage. The two halves of the ship had to split apart in a fraction of a second, triggered by explosive devices firing simultaneously. 4 explosive bolts at the 4 corners connecting the two halves, and explosive guillotines slicing through the entire bundle of wiring and plumbing, and the ascent stage would fly up while the descent stage remained behind. The entire process happened in less than 1 second. In that window of time, if the ascent stage's attitude control system didn't function precisely, if the small thrusters didn't fire in exactly the right direction, at exactly the right amount, at exactly the right moment, the ascent stage could begin to spin. Not a gentle rotation that could be corrected, but an uncontrolled tumble, like an aircraft falling into a spin it cannot recover from. And while the ascent stage was tumbling out of control, directly below it, the descent stage was still there, not moving, not able to get out of the way. Impact. Residual hypergolic propellant remained in the descent stage's tanks, Aerozine 50 and nitrogen tetroxide still sitting in their containers. When those two substances made contact through the impact, the reaction would be instantaneous. Engineers calculated the explosion would occur within 1/10 of a second of impact. No time to realize what was happening. No time to report to Houston. No time for anything at all. Just sudden silence on the radio frequency. And on the monitoring screens in Houston, every one of Eagle's readings would simultaneously drop to 0 in the same second. These were 3 scenarios for which none had a rescue option. No second ship waiting in orbit, no second Saturn V on a launch pad, no rescue team training for a lunar emergency. The Apollo program in 1969 did not have, and could not have, any of those things. If any one of those 3 scenarios occurred, Houston would know. The whole world would know. And no one could do anything except watch. That is why a piece of plastic the size of a fingertip, lying in the lunar dust beneath Eagle's floor, mattered so much. Not because the plastic itself was dangerous, but because it was the final link in a long chain, and if that link wasn't reconnected, the entire chain would break. And Buzz Aldrin knew that. He knew the 3 scenarios. He knew there was no rescue option. He knew that everything depended on that circuit being closed before liftoff. So he reached into his shoulder pocket and pulled out a pen. Morning of July 21st, 1969. Houston had been awake all night. Armstrong and Aldrin had managed a few broken hours of sleep. Liftoff was scheduled for 5:54 p.m., still about 8 hours away, and the circuit breaker problem was still not fully resolved. Houston had found the secondary wire, in theory usable, but no one was certain, and in those remaining 8 hours, a question hung in the air that no one said aloud. Was there still another way? Aldrin was staring at the small hole in the instrument panel, the gap where the plastic tip of the circuit breaker had broken away. Inside that gap were 2 small metal contact points. When the plastic tip had been intact and pushed in, it would press those 2 contacts together, closing the circuit, sending the ARM signal to the engine. Now the plastic tip was gone. The 2 contacts were open, separated by a few millimeters, not touching, the circuit dead. Physically, the problem was simple. Something needed to fit into that gap, firm enough to press the 2 contacts together and stay in place throughout the entire liftoff sequence. But Aldrin knew one critical thing. Whatever it was, it could not be metal. The reason was simple but decisive. If he used a metal object, a ballpoint pen with a metal casing, a piece of wire, anything conductive, and inserted it into that area incorrectly, the metal could simultaneously touch both contact points in an unintended way. That could create a wrong electrical connection, not closing the ARM circuit, but shorting out part of the ship's electrical system. In electronics, the short circuit doesn't always produce sparks or smoke. Sometimes it quietly destroys a chip, damages a relay, or sends a false signal to another system. And on a spacecraft where every system is interconnected, a small short could propagate in ways impossible to predict, replacing a solvable problem with an unsolvable disaster. Aldrin didn't want to risk that. He needed something non-conductive, firm enough to press the contact, thin enough to fit into the small gap, and available in the cabin right now. He reached into the shoulder pocket of his spacesuit. That pocket held the small things astronauts carried for use during flight: pens, a small notebook, a few personal items. Small, light, taking up no space. And in it was a felt tip marker. Not high technology, not a special NASA device. An ordinary Duro felt tip marker, the kind you could buy at any office supply store in America in 1969. Plastic body, felt nib saturated with ink, non-conductive, firm enough, thin enough. Aldrin took the pen, looked at the hole in the instrument panel. He guided the tip of the pen into the gap, carefully, slowly, without rushing. Not because he wasn't worried, but because this was not the moment to rush. Any unnecessary movement could damage something else on the panel. The pen tip made contact with the interior contact point. He pressed gently. A small click. Circuit breaker, engine arm, was back in position. That was all. No lights came on, no loud confirmation tone, just a small click in a silent room on the moon, and the feeling as Aldrin released his hand and looked at the pen still sitting in the gap, holding its position. The circuit was closed. He reported to Houston. Houston confirmed. The ARM signal was being received. But here is the part that many people don't know. Later, in the post-flight technical debriefing, Neil Armstrong said this. He believed that even without the pen, the circuit breaker might have closed on its own during the automated startup sequence. Eagle's electrical systems were designed with certain automatic checks before liftoff, and in that process, there was a possibility the electrical signal would have been strong enough to activate the ARM circuit, even through the secondary path Houston had found. Armstrong called using the pen correct, but possibly unnecessary. Perhaps everything would have been fine without it. Perhaps not. And this is the most important thing about the entire story. Not the pen, not the circuit breaker, not any technical detail, but Aldrin's decision in that moment. He didn't know whether the secondary wire would work. He didn't know whether the automated system would be strong enough to close the circuit. He didn't know whether the pen was truly necessary. He only knew one thing. He had in his hand a simple, safe, non-conductive solution, and using it carried no risk at all. When you are on the moon, 384,000 kilometers from anyone who could help, you don't gamble on perhaps. You use the pen. That Duro felt tip marker and the broken engine arm circuit breaker are now on display at the Museum of Flight in Seattle, Washington. Two small objects in a glass case, unremarkable to look at, no spotlight on them, no dramatic signage, just an old felt tip marker and a broken piece of plastic. And the story of that night. There is one more thing to say about this pen, and this is the moment a famous legend needs to be corrected. If you have ever heard the story that the Fisher space pen, the special pen NASA developed to write in zero gravity, saved Apollo 11, know that this is a marketing story that has circulated for decades without basis in fact. The Fisher AG-7 space pen was on board Apollo 11, true, but it was not what was used to fix the circuit breaker. Aldrin used his ordinary Duro felt tip marker from his pocket, not special technology, not a NASA device, not something designed for space. Sometimes the thing that saves lives is not the most advanced technology available. Sometimes it's just what you find in your pocket. But while Aldrin was solving his problem down below, 60 miles above the lunar surface, Michael Collins was alone inside Columbia, and he was facing an entirely different kind of solitude. 60 miles, about 97 kilometers straight up, from the lunar surface where Eagle was parked to the orbit where Columbia was flying. Not a large distance by space standards. On Earth, 97 kilometers is a short drive, the distance from one city centre to the next. Something you can look at on a map and think, oh, that's close. But 97 kilometers straight up, in the vacuum of space, between two objects moving in different orbits, is a distance that cannot be crossed by anything other than a rocket engine, working with precise accuracy. And Michael Collins understood that more clearly than anyone. Collins was the third astronaut of Apollo 11, the one most of the world nearly forgot in the rush of that historic moment. While Armstrong stepped down onto the lunar surface and spoke the words that entered history, Collins was flying circles above. While Aldrin planted the flag and took photographs and collected moon rocks, Collins was watching radar screens and writing in his notebook. While the world celebrated, Collins was alone in an even smaller metal box, more isolated than any human being had ever been. NBC called him the loneliest man in history. Their correspondent said on air that not since Adam has any human known such solitude. Collins read those words later and found them amusing. In his memoir, Carrying the Fire, widely considered the finest astronaut memoir ever written, he recorded that he did not feel lonely. He felt part of what was happening below. He was monitoring, preparing, ready. But that didn't mean he wasn't afraid. Collins carried a small notebook tied around his neck with a cord. Inside that notebook were 18 contingency rendezvous plans, 18 different procedures for 18 different situations that might arise when Eagle attempted to fly up and meet Columbia. 18 plans, not 5, not 10, 18. Each plan was numbered, handwritten, memorized by Collins to the point where he could execute them in the dark without looking at the page. Plan 1 for the case. Eagle launched on time and into the correct orbit. Plan 2 for Eagle. launching 30 minutes late. Plan 3 for the case. Eagle's engine underperformed, not enough thrust. Eagle entering a lower orbit than planned. And Plan 18, for the situation where Eagle couldn't fly up to meet Columbia on its own, and Collins would have to lower Columbia to a lower orbit to attempt reaching Eagle from above. This was an option never tested in actual spaceflight, never fully simulated. No one knew for certain whether it was even feasible, because manual rendezvous in low lunar orbit, with two spacecraft moving at thousands of miles per hour, was a problem that even the most powerful computers of that era couldn't calculate easily. Collins was prepared to try, if needed. Each orbit around the Moon took about 2 hours. Within each orbit, there was a particular stretch of time Collins called the far side, when Columbia flew around the dark side of the Moon, completely hidden behind that enormous rock. During that time, about 45 minutes per orbit, no radio signal could travel in or out, not because equipment had failed, but because the Moon was blocking the path between Columbia and Earth. Radio waves don't pass through rock. 45 minutes of total silence. No Houston, no Armstrong, no Aldrin, no human voice at all. Just the soft hum of the machinery inside the ship, the sound of his own breathing, and the darkness of the Moon's far side outside the window. Collins later described those periods not with the word lonely or frightened. He used the word aware, conscious. He became acutely aware of his position in space, of there being no one else nearby, of the absolute silence surrounding him. And on those passes around the far side, when he knew Eagle had a problem with the circuit breaker, when he knew liftoff was not certain, those 45 minutes stretched far longer than usual. But Collins also held a truth he had written plainly in his memoir, a truth few astronauts have dared say publicly. If Armstrong and Aldrin could not leave the Moon, he would fly Columbia home alone. Not because he didn't care about his crewmates, but because he understood the reality clearly. Staying in lunar orbit and waiting would change nothing. Columbia had a finite fuel supply, a finite oxygen supply, a finite window of time, and no miracle could happen if he kept flying in circles. He wrote, "I would not commit suicide, I would come home." Then he added a line that is hard to forget once you've read it. "But I knew I would be a marked man for the rest of my life." Not because he had done anything wrong, but because history is not fair to survivors. Amundsen reached the South Pole before Scott, but Scott's tragic death cast a shadow over Amundsen's achievement in the public eye. Collins understood that. He would return. He would live. And for the rest of his life, people would ask him, "How did it feel to leave your crewmates behind on the Moon?" Even though he hadn't left anyone, even though he'd had no other choice. But Collins was not the only one watching Apollo 11 from a distance that night. Somewhere else in the Moon-Earth-Sun system, another probe was making unusual orbital passes. Not NASA's, not American, and no one on Eagle knew exactly what it would do next. Step back for a moment. Go back to July 13th, 1969. 3 days before Apollo 11 left the launch pad at Kennedy, Florida, another rocket had already lifted off. Not from Florida, not from any location the public knew about, from a secret facility in Kazakhstan, Soviet Union, a place whose existence the Soviet government did not officially acknowledge for decades. That rocket was carrying an unmanned probe, its name, Luna 15. To understand why Luna 15 mattered, you need to understand the context of the space race at that moment. By 1969, the Soviet Union had lost the race to put humans on the Moon. They knew it. Their N-1 rocket program, the Soviet equivalent of the Saturn V, had failed in its first test in February 1969, exploding on the launch pad. A second test in July 1969, just weeks before Apollo 11, also failed, creating one of the largest non-nuclear explosions in history and completely destroying the launch facility. Putting people on the Moon before the Americans, no longer possible. But there was something else, a smaller target, but one that still held enormous symbolic value: lunar soil. The concept behind Luna 15 was both simple and audacious. Instead of sending humans to the Moon to collect samples, something the Soviet Union could no longer do, they would send a robotic probe, It would land, use a mechanical arm to scoop a quantity of lunar soil into a return container, then launch directly back to Earth. No astronauts needed, no complex life support systems, no worry about bringing people home safely. If it succeeded, the Soviet Union would have lunar samples in hand before Apollo 11 returned to Earth. Scientifically, this didn't matter much. Who collected samples first was less important than what the samples revealed. But as propaganda and political symbolism, it was a win that could partially overshadow Apollo 11's achievement. The Americans put men on the moon, but we brought back lunar soil first. That was the message Moscow wanted to send. Luna 15 reached lunar orbit on July 17th, 3 days before Eagle landed, and from the very beginning, nothing was going according to plan. The probe made orbit after orbit around the moon, far more than originally planned. Soviet engineers were trying to calculate the optimal landing point, adjusting the trajectory, preparing for descent. But the data they had about the lunar surface, terrain maps, altitude readings, slope angles, wasn't accurate enough. They didn't know precisely where they were landing. On the other side of that race, Armstrong and Aldrin standing on the surface of the moon, they occasionally tracked Luna 15 passing overhead. Not with the naked eye, the probe was too small and its orbit too high to see directly. But through radar systems and information from Houston, they knew it was there. A Soviet probe flying circles above their heads while they were walking on the moon. 2 missions from 2 superpowers unfolding simultaneously in the same region of space with entirely different objectives. Houston had one concern. Would Luna 15 interfere with Eagle and Columbia's rendezvous orbit? Would the Soviet probe fly into the path Eagle would need to use when meeting Columbia? The tension ran high enough that, in one of the Cold War's rare moments of openness, NASA directly contacted the Soviet Space Agency and asked outright, "What orbit is Luna 15 in right now?" The Soviets answered. They provided orbital data, something that had never happened in the entire decade of space competition that preceded it. 2 rivals, in one brief moment, cooperating to avoid a collision in lunar orbit. July 21st, 1969, the same day Armstrong and Aldrin were preparing for liftoff. After 52 orbits, more than double the original plan, Soviet engineers made their decision. It was time to go. If they waited any longer, Apollo 11 would return to Earth first, and the entire point of the mission would be gone. Luna 15 began its descent. The probe slowed, lowered its orbit, began approaching the surface. Engineers in Moscow watched the telemetry signal, numbers and graphs showing the probe's condition in real time. And then, at an altitude of a few kilometers above the surface, the signal changed abruptly. Not in the way they had hoped. Luna 15 struck the slopes of Mare Crisium, the Sea of Crises, at approximately 300 miles per hour. Not a landing, an impact. A probe worth hundreds of millions of rubles, carrying the hopes of an entire space program, 3 years of design and construction, 52 patient orbits, ended in one instant, in a cloud of lunar dust that rose and fell back down in the soundless vacuum. The distance from Luna 15's impact point to Tranquility Base, where Eagle was parked, was approximately 500 kilometers. Same moon, same day, 2 entirely different fates. Moscow said nothing about the failure for days. While the entire world was watching Apollo 11 prepare for liftoff, information about Luna 15 was kept completely secret. Only years later, when the Soviet Union collapsed and documents were declassified, did the world learn the full story of that probe. The space race, at least this chapter of it, had ended in a small crater on the surface of the moon, with no witnesses, no sound, no announcement of defeat. Just lunar dust rising, then settling back down. And 500 kilometers away, inside a small metal box with a felt-tip pen holding a circuit breaker in position, 2 men were counting down to the most important moment of their lives. 5:54 p.m. Houston time. Liftoff. 5:54 p.m., July 21st, 1969, Houston time. At Mission Control, Capcom Ron Evans, the astronaut seated at the communications console, the only person authorized to speak directly with the crew during this critical phase, picked up his microphone. Tranquility Base, Houston. you are cleared for takeoff. Tranquility Base, Houston, you are cleared for takeoff. A short sentence, so ordinary it sounded like air traffic control clearing a commercial flight from a runway. Aldrin responded, and his reply became one of the most quoted lines in the history of space exploration, though far fewer people know it than know Armstrong's words. Roger, understand, we're number one on the runway. We're number one on the runway. There was no runway there, no control tower, no runway lights, just the grey, dusty surface of the moon, Eagle's descent stage, which would stay behind forever, and two men standing in the ascent cabin, hands on the instrument panel, eyes on the displays. And in a small gap on the instrument panel, a Duro felt tip marker holding its position. Before the engine could fire, Eagle had to do something that sounds technically straightforward, but was psychologically one of the strangest moments of the entire mission. It had to split in two. The ascent stage had to separate from the descent stage. The two halves of the ship, joined together since Eagle left Earth, had to come apart in less than 1 second, triggered by a series of explosive devices firing simultaneously. 4 explosive bolts at the 4 corners connecting the two halves all had to fire at the same moment, within thousandths of a second of each other. If one fired later than the rest, the uneven force would tilt the ascent stage in the instant of separation, and tilting in that instant could cause problems impossible to predict. 2 deadface connectors, large electrical couplings, had to be severed to cut power between the 2 stages, and finally, a device engineers called an explosive guillotine would slice through the entire bundle of wiring and plumbing connecting the 2 halves, like a blade falling to cut a rope. An explosive guillotine, on a spacecraft, on the moon. That was the engineering of 1969. Aldrin counted down. 9, 8, 7, 6, 5. Abort stage, engine arm, ascent, proceed. Not a Hollywood countdown, from 10 to 0 with rockets blazing and crowds cheering. This was a sequence of technical commands, each word triggering a specific action in the computer systems in exactly the programmed order. The bolts fired, the guillotine cut. And in that moment, a moment that every astronaut who flew a lunar module described the same way, the ascent stage dropped about an inch before the engine caught up. Not freefall, not dangerous, just lunar gravity acting in the tiny window between the bolts firing and the engine generating enough thrust to overcome it. But that feeling, the small drop downward before flying up, was something no lunar module pilot ever forgot. Charlie Duke, lunar module pilot on Apollo 16, described the moment. My heart jumped into my throat. Then the engine fired. Not like the Saturn V igniting, no enormous roar, no towering column of flame. Hypergolic propellant doesn't burn that way. It reacts instantly, more quietly, and in the vacuum of the moon, no sound travels outside the ship at all. Inside the cabin, Aldrin felt the thrust, not as violent as Saturn V launching from Earth, but enough to press him gently against the floor, enough to feel that everything was working. Armstrong spoke 4 words over the radio. The Eagle has wings. Aldrin looked out the small left window. Below, Eagle's descent stage was retreating. More accurately, Eagle was flying up and the descent stage was standing still. But from his perspective, it looked as though the lower half of the ship was sinking into the lunar dust. And he saw something no human being had ever seen before. The exhaust plume from the ascent engine, invisible in the vacuum but carrying real force, was striking the descent stage below, and that force was tearing apart the gold insulating blanket wrapped around the descent stage's exterior, the foil-thin material Grumman had used to reduce weight, and blowing it outward in all directions like golden sheets of paper caught in a wind. Shimmering gold fragments scattered across the lunar surface, falling slowly in the low gravity, like autumn leaves in a garden where there is no breeze. Then Aldrin saw something else. The American flag, planted by Armstrong and Aldrin only a few dozen hours before, about 25 feet from Eagle, was beginning to lean. The flagpole was aluminium, driven only about 6 to 8 inches into lunar soil that had turned out to be harder than expected. The horizontal crossbar at the top, designed to open out and hold the flag upright, had jammed when Armstrong tried to extend it, leaving the fabric bunched and wrinkled in all those famous photographs. That's why the flag appears to be waving in a breeze in every iconic image. Not because there's wind, but because the stuck crossbar locked the fabric into a permanent wrinkled shape. The exhaust plume pushed against the flagpole leaned, then fell. Aldrin watched that moment through the small window. He said nothing to Armstrong. He didn't report it to Houston. He just watched and remembered. He recounted it later. I chose not to say anything to Neil. There was nothing that needed to be said at that point. It is the only Apollo flag that came down. All flags from Apollo 12 through Apollo 17 still stand, confirmed by photographs taken by NASA's Lunar Reconnaissance Orbiter decades later. Only the Apollo 11 flag, the first flag, the flag of the most historic mission, fell. No one witnessed it except Aldrin, and he kept it to himself throughout the ascent. The engine burned for 435 seconds, just over 7 minutes. In those 7 minutes, Eagle went from a liftoff weight of approximately 10,300 pounds, with the moon's low gravity, 3,500 pounds of thrust was enough to lift it, to roughly 5,900 pounds when the fuel was spent. The ship grew lighter, grew faster. Armstrong noted one anomaly during the ascent. Eagle was rolling gently side to side, a motion pilots call Dutch roll. Not dangerous. Tom Stafford and Gene Cernan had experienced the same thing during Apollo 10 2 months earlier and had warned Armstrong about it. He knew what to do. Hold steady, let the control system correct itself. After 435 seconds, the engine cut off. Eagle was at an altitude of roughly 60,000 feet and flying in an elliptical orbit around the moon. Houston confirmed with 3 independent guidance systems: correct orbit, correct velocity, everything within limits. Armstrong transmitted the final report of the liftoff phase. The Eagle is back in orbit, having left Tranquility Base. The Duro felt tip marker had held its position through all 435 of those seconds. It had not fallen out, had not shifted, had not caused a single electrical fault. An ordinary pen, in a small gap, through the roar of an engine and the vibration of liftoff, had done exactly the one thing it needed to do. But Eagle was not home yet. Columbia was somewhere above, and the chase across lunar orbit had only just begun. Eagle was flying, but flying didn't mean safe. Picture it this way. You've just jumped out of a building, and somewhere above you, an elevator is moving. Your goal is to land exactly in the elevator doorway as it opens. Not while it's standing still, while it's moving, at a speed you can't track with the naked eye. That was the problem Armstrong and Aldrin had to solve in the next 3 hours and 41 minutes. Columbia was not standing still waiting for Eagle. It couldn't stand still. In lunar orbit, standing still means falling toward the surface. Collins was flying a circular orbit about 69 miles above the surface, at roughly 3,700 miles per hour. Every second, Columbia was moving about 5,400 feet. Eagle, having just left the surface, was flying in a lower elliptical orbit, lowest point about 11 miles, highest point about 53 miles. Eagle's velocity was lower than Columbia's because its orbit was lower. 2 spacecraft, 2 different orbits, 2 different velocities, and they had to meet at one specific point in space, at one specific moment, with a relative velocity small enough to allow docking. This was the problem orbital engineers at Houston had been calculating for months before the flight. And now, with Eagle actually flying, those calculations had to be executed in reality, step by step, burn by burn, adjustment by adjustment. The reason Eagle had to chase Columbia, rather than Columbia chasing Eagle, lies in one of the most counterintuitive principles of orbital mechanics. In orbit, a spacecraft flying lower actually flies faster, not slower, faster. This holds true for every object in orbit, from artificial satellites to the moon around Earth. A lower orbit means the object must move faster to maintain its circular path, counteracting the stronger gravitational pull at lower altitude. So Eagle, in its lower orbit, would gradually catch up with Columbia in its higher orbit. But if Eagle fired its engine to climb up to Columbia's altitude, it would slow down and never catch up. This is the paradox of orbital mechanics. To catch someone ahead of you, sometimes you have to fly lower than them. About 57 minutes after liftoff, Eagle performed its first engine burn. Not the ascent engine that had shut down after 435 seconds and would not be used again. Instead, the 16 small thrusters mounted on the hull, each producing only a few dozen pounds of thrust, designed for orbital adjustments and attitude control. The first burn lasted about 76 seconds, enough to raise Eagle's lowest orbital point from about 11 miles to roughly 52 miles, creating a nearly circular orbit. The goal was to place Eagle in an orbit close to Columbia's, but still slightly lower, just enough to keep closing the gap. The second burn, smaller, only a few seconds, to refine it further. The third burn, the most important, placed Eagle on an intercept trajectory, a calculated flight path that would bring Eagle to Columbia's exact position after roughly 2 more orbits. Meanwhile, Collins was tracking from Columbia. He activated the radar system VHF ranging and began measuring the distance to Eagle. The numbers on the radar display fell steadily with each passing minute: 250 miles, 180 miles, 120 miles. The notebook with 18 contingency plans was still in his hand. He read through Eagle's orbital parameters, comparing them against what he had prepared. Everything was tracking Plan 1, the best plan, the plan that required no contingencies at all. Collins didn't put the notebook down, but he allowed himself to breathe a little easier. About 3 hours after liftoff, Eagle and Columbia were a few dozen kilometers apart, close enough for Collins to see Eagle through Columbia's optical tracking scope. He raised his camera and took a photograph that would become one of the most viewed images in human history. Not because it is beautiful in any conventional sense, but because of what it means once you understand it. In the frame, Eagle, small, fragile, wrapped in its crinkled gold insulating blanket, flying in the darkness of space. Behind Eagle, curving along the lunar horizon at the bottom of the frame, the grey surface of the moon. And behind everything, farther away, larger, blue and white and impossible against the absolute black of space, Earth. A small sphere, hanging there, nothing holding it up. Collins wrote about that photograph later. Every human being who has ever lived is in that picture, except me. Stop and think about that for a moment. Every person you have ever known, every person who ever existed in history, Caesar, Cleopatra, Shakespeare, Einstein, every child born that day, every elderly person lying in a hospital bed, every person eating dinner, sleeping, watching television, celebrating Apollo 11, all of them were in that photograph, in that small blue sphere in the upper corner of the frame, and the only person not in it was the one holding the camera. Collins, the loneliest man in history, the one the world nearly forgot, the one whose name people had to look up, was the person who took the only photograph in which every single human being appears. The distance between the two ships kept falling. 25 miles, 12 miles, 6 miles. At about 5 miles, Collins could see Eagle clearly through the tracking scope. No longer just a moving point of light against the black, but a recognizable shape. The strange box with 4 landing legs still attached below, the gold insulating panels torn and ragged from the exhaust plume of liftoff. At 1 mile, Collins switched to manual control. The computer had done the hard part. What remained, the final, slow, careful part, was human work. 1 mile. In space, 1 mile sounds close. On Earth, it's a 10-minute walk, a distance where you can see a person standing at the far end of a long, straight road. But in lunar orbit, where 2 spacecraft are flying at thousands of miles per hour, where a small miscalculation in relative velocity can turn approach into collision in seconds. 1 mile demands total concentration. Collins switched off the autopilot. From here, he flew manually. Docking in space is unlike anything on Earth. No friction. No gravity pulling 2 objects naturally toward each other. Every movement one ship makes, however small, continues indefinitely until another force acts to stop it. That means, if Collins pushed Columbia toward Eagle too hard and didn't brake in time, the 2 ships would collide with enough force to cause damage. If he braked too early, the 2 ships wouldn't make contact, and the entire approach would have to be restarted from the beginning. The ideal approach speed for docking was about 0.3 meters per second relative velocity, slower than a human walking pace, roughly the speed at which you reach out and touch a door when you want to open it. At that speed, Collins had to guide Columbia to the exact position where the probe, a cone-shaped metal rod attached to Columbia's nose, would slide into the drogue, a funnel-shaped socket attached to Eagle's top. The probe had to enter exactly at the center of the drogue. A deviation of a few centimeters was enough to prevent the capture mechanism from engaging. But there was a small problem Collins noticed as Eagle closed to within a few dozen meters. Eagle's attitude wasn't perfectly aligned with Columbia. Not by much, just a few degrees off. But a few degrees at that distance was enough to prevent the probe from entering the drogue at the required angle. Collins used Columbia's thrusters to rotate the ship gently, a small correction measured in milliseconds of thruster burn. Checked the alignment, rotated a little more, checked again. Armstrong watched from inside Eagle, looking through the small window. He looked like someone driving very carefully through a narrow alley, Armstrong said later. At about 30 feet, Collins could see Eagle's drogue clearly through the docking scope, a small metal ring, the center of every ounce of concentration in that moment. He nudged Columbia forward, gently, slowly, patiently. The probe approached the drogue, made contact, and in the next instant, a small click as the 3 capture latches on the probe head engaged with the drogue rim, called soft capture. The 2 spacecraft were connected, but only by 3 small hooks, enough to hold them together, not enough to seal them completely. Collins activated the retraction mechanism. The probe pulled back, drawing the 2 ships together until the 12 hard latches on Columbia's docking mechanism engaged with Eagle. A rapid series of click, click, click. Quick, firm, unmistakable. Hard dock. 3 hours and 41 minutes after Eagle left the surface of the moon, Collins wrote in his memoir, "This is the first time since we left Earth that I have allowed myself to feel genuine relief. Not when Saturn V launched successfully, not when Eagle landed safely, not when Armstrong took his first step on the lunar surface, but this moment, when the 12 hard latches locked and he knew that 3 men were in the same place, the same ship, the same orbit. He had been waiting for this moment for 195 hours, from the instant Apollo 11 left the launch pad at Kennedy. Armstrong cracked a joke over the intercom about the slight wobble during docking. Collins laughed. It was the first sound that wasn't a technical report or a parameter confirmation in many hours. The next 2 hours unfolded in a careful, methodical process. Armstrong opened Eagle's hatch, the small round door connecting Eagle to the docking tunnel, a tube about 32 inches long joining the 2 ships. He crawled through the tunnel, carrying the most important cargo of the entire mission, lunar samples. 47.5 pounds, roughly 21.5 kilograms, of rock and soil collected during the moonwalk, sealed inside specially designed containers built to prevent any gas or microorganism from Earth contaminating them. Scientists in Houston had been waiting for those samples for years of mission preparation. Along with them, rolls of film, hundreds of photographs taken on the lunar surface using special Hasselblad cameras, not digital cameras, actual film that needed to be developed in a darkroom after returning to Earth. If the film was damaged during transport, those images would be gone forever. Armstrong passed everything through the tunnel. Collins received it and stowed it inside Columbia. After everything had been transferred, including Armstrong and Aldrin themselves, it was time to say goodbye to Eagle. Not an emotional farewell, no ceremony, just a step in the checklist. Close the docking tunnel hatch, verify the seal, and activate the release mechanism. Eagle was let go. The small ship, the ascent stage with no descent stage left, no meaningful fuel remaining, no one inside, drifted away from Columbia and began flying free in lunar orbit. Collins watched through the window as Eagle slowly receded. No one said anything for a few seconds. Eagle, the ship that had carried 2 human beings down to the moon and brought them back, was flying alone for the last time, in the alternating darkness and light of lunar orbit. Its orbit would gradually decay in the weeks and months ahead, until the moon's gravity pulled it down and it impacted the surface somewhere. No one knows exactly where. Or perhaps not. But that is the story of the next part. Tranquility Base, July 21st, 1969, after 5:54 p.m. From the moment Eagle left, the surface of the moon at that point fell completely silent. No wind to blow away the traces, no rain to wash away the footprints, no seasonal temperature changes to crack or warp the objects left behind. Just absolute vacuum, solar radiation, and a silence with no end in sight. Everything Armstrong and Aldrin left there is still there, exactly as they left it. The largest and most visible thing, Eagle's descent stage. 4 landing legs still standing on the grey, dusty surface. The hull, gold insulating panels torn and ragged by the exhaust plume from liftoff, still there. The descent engine cover at the centre of the hull. The equipment bays with their doors hanging open since Armstrong and Aldrin removed the instruments before their moonwalk. Eagle's descent stage is the first human-made object left on the surface of the moon by people. It will remain there for billions of years, longer than any structure human beings have ever built on Earth, longer than the pyramids, longer than the Great Wall, longer than anything we can meaningfully imagine. In 2009, 40 years after Apollo 11, NASA's Lunar Reconnaissance Orbiter flew over Tranquility Base and photographed it from orbit. In those images, you can see the descent stage clearly, a small shadow, the unmistakable shape of a lunar lander, standing alone on the grey dust. Around it, darker streaks, the tracks left by Armstrong and Aldrin during their moonwalk, still visible 4 decades later. Not far from the descent stage, still working to this day, the laser-ranging retroreflector. This is a special mirror, not the ordinary kind you look into to comb your hair. It is an array of corner cube prisms, engineered to reflect laser light back in exactly the direction it came from, regardless of angle. Shine a laser at it from any direction, and the beam reflects straight back to its source. Since 1969, astronomical observatories around Earth, in California, Texas, France, Italy, Japan, have regularly fired laser pulses toward the moon, aimed at the exact coordinates of Tranquility Base. The laser travels 384,000 kilometers to the moon in about 1.28 seconds, strikes the mirror, reflects back, and 1.28 seconds later, the return pulse is detected by a telescope on Earth. By measuring the precise round-trip travel time, scientists can calculate the distance from Earth to the moon with accuracy down to the nearest millimeter. Not kilometers, not meters, millimeters. And from those measurements, we know something no one knew before 1969. The moon is drifting away from Earth at roughly 1.5 inches per year. Not fast, but steady, never stopping. Something left on the moon in 1969 is still helping us understand the universe better every day, more than half a century later. The other things left behind had no scientific function. They were simply things that had to be left. 2 PLSS units, the portable life support backpacks that Armstrong and Aldrin wore during the moonwalk, including the very backpack that had caused the events of that night. Left behind to reduce weight for liftoff, every pound saved meant the ascent engine needed less fuel, meaning Eagle could fly higher and faster to meet Columbia. 2 pairs of lunar overshoes, the outer protective covers worn over the spacesuit boots, designed for walking on the lunar surface and discarded when no longer needed. Still there, still intact. Nothing to degrade them. A Hasselblad camera body with no film inside, because the film had been removed and brought back on Columbia. The camera was left because its weight wasn't worth carrying home, and NASA had calculated that the scientific data in the film rolls mattered more than the camera housing. And there are things left behind not because of weight, but because of meaning. A memorial patch honouring the 3 Apollo 1 astronauts, Gus Grissom, Edward White, and Roger Chaffee, who died in a launchpad fire on January 27, 1967. 2 years before Apollo 11, they had given their lives testing the spacecraft systems on the ground. No chance to escape, no warning, just fire in a cabin designed to hold pure oxygen, and pure oxygen burns faster than anything you can imagine. Apollo 11 reached the moon partly because of them, because of what was learned from that disaster, because of the design changes made in its aftermath. Leaving the patch was Armstrong and Aldrin's way of saying, "We have not forgotten." Two small medals honouring two Soviet cosmonauts, Yuri Gagarin, the first human in space, killed in a plane crash in 1968, and Vladimir Komarov, who died when his Soyuz 1 spacecraft malfunctioned and fell back to Earth in 1967. Two rivals at the height of the Cold War, honouring the dead from the other side. No one asked Armstrong and Aldrin to do this. It wasn't in the checklist. It wasn't in the mission plan. They chose to, because they wanted to. And finally, one small thing Armstrong almost forgot to leave. A silicon disc about 1.5 inches across, smaller than a 50-cent coin. Etched onto it by laser were messages from 73 heads of state and world leaders, each message reduced to a scale readable only under a microscope. 73 countries, 73 languages, 73 ways of saying the same thing. We were here. We looked up. And we wanted you to know this moment belongs to all of us. Armstrong nearly forgot to leave it. He was already on the ladder climbing back into Eagle when Aldrin reminded him, "Neil, the disc." Armstrong turned back, retrieved the disc from his pocket, and tossed it gently onto the lunar surface. Not placed carefully, no ceremony, just a gentle toss, and the disc fell slowly in the low gravity and settled somewhere in the dust near the descent stage. Exactly where, no one knows. No photograph was taken, no GPS coordinates. It's there, but in the wide grey dust surrounding the descent stage, a 1.5-inch disc is something that cannot be found without going there and searching. And then there are the footprints. Armstrong and Aldrin's footprints, pressed deep into the fine lunar dust, detailed enough that you can see every ridge pattern of the spacesuit boot sole. No wind on the moon to erase them, no rain, no weather, no creatures passing through, only solar radiation. And radiation doesn't erase footprints. It only slowly alters surface colour over millions of years. Scientists calculate those footprints will remain intact for at least 50 million years, unless a meteorite strikes that exact location, or unless humans return and accidentally step on them. 50 million years. The dinosaurs went extinct just 66 million years ago, and you are living in a time when those footprints have existed for just over 55 years. After Apollo 11, 6 more missions were sent to the moon. One of them, Apollo 13, never landed. An oxygen tank explosion on the way to the moon forced the crew to abandon the landing plan and use the lunar module as a lifeboat to return to Earth. That story alone could fill hours of its own. But the remaining 5 missions, Apollo 12, 14, 15, 16, and 17, all landed successfully, and all lifted off successfully from the surface of the moon. 6 landings, 6 liftoffs. Not one failure. The ascent engine, that engine so simple it was almost primitive, no turbo pump, no throttle, no gimbal, just 2 valves and hypergolic fuel, worked perfectly every single time. Not one malfunction, not one moment where a backup plan had to be activated, not one moment where an astronaut had to wonder whether the next second would be their last. 6 for 6. What does that mean? It might mean Bell Aerosystems was right, that simplicity truly is the highest form of reliability, that when you strip away enough things that can fail, what remains won't fail. But there is another way to look at it, a way engineers don't like to say aloud because it doesn't sound scientific. We were fortunate. Not fortunate in the sense that nothing was worth worrying about, but fortunate in the sense that many things could have gone wrong and none of them did. That is worth thinking about, not to feel anxious, but to feel grateful. Consider the numbers. The ascent engine of each lunar module was never test-fired before flight, not because the engineers were careless or negligent, but because hypergolic propellant is extremely corrosive. Each test firing meant exposure to aerosine 50 and nitrogen tetroxide, 2 substances that corrode metal, corrode rubber, corrode nearly everything they touch. After a single firing, the valves and plumbing inside the engine could be microscopically damaged, invisible to the eye, but enough to affect performance. So each ascent engine was fired exactly once in its entire life. That once was when an astronaut pressed the start button on the moon. 6 times, 6 different engines, 6 first and only firings in the life of each engine, and all 6 worked. When you know that, when you understand that every liftoff from the moon was a first test of an engine that had never actually run before, Armstrong's words take on far more weight. The Eagle has wings. He didn't know that for certain until it actually happened. And here is the strangest thing about this entire story. Bell Aerosystems' design philosophy, high reliability through simplicity, is not widely used in modern engineering. If anything, the trend over recent decades has been to add more backup systems, more sensors, more layers of checking, more monitoring software. Each addition is justified by reasonable logic. It makes the system safer. But each addition is also one more thing that can fail. And sometimes, not always, but sometimes, the simplest thing is the most reliable thing. A felt tip marker instead of a complex electronic system. 2 liquids touching each other instead of an elaborate ignition mechanism. Pressure feeding instead of a turbo pump with thousands of moving parts. Sometimes less really is more. But that philosophy only works when you understand deeply enough to know what you're removing and why removing it is safe. Not removing things out of laziness or to cut costs, but removing things after carefully analysing every failure point and concluding that the risk of complexity is greater than the risk of simplicity. That is the difference between intelligent simplicity and careless simplicity. Bell Aerosystems chose intelligent simplicity, and 6 times on the moon, that choice was proven right. There is one question that to this day has no certain answer. Eagle, the ascent stage of Apollo 11, the ship that carried Armstrong and Aldrin from the lunar surface to orbit, after being released from Columbia, where did it go? NASA originally believed its orbit would gradually decay and it would impact the moon within a few months. Unlike the ascent stages of Apollo 12, 14, 15, 16 and 17, all of which were deliberately deorbited and crashed into the moon to generate seismic readings for instruments placed on the surface, Apollo 11's Eagle was simply released. No controlled deorbit burn, just let go and left to drift. And no one tracked it long enough to know where it ended up. But in 2021, an independent researcher named James Medaw published calculations suggesting something unexpected. Based on a detailed gravitational model of the moon, including regions of uneven mass density beneath the surface, called mass concentrations or mascons, which create small variations in gravitational pull that can affect orbits in ways simple models can't predict. Medaw calculated that Eagle may still be in orbit around the moon to this day. Not crashed into the moon, not gone, but still flying after more than 55 years, still making silent orbits around the world it once landed on and left. This calculation has not been officially confirmed by NASA. To confirm it, you would need to track the orbit of a small, non-transmitting object in low lunar orbit, something not easy to do even with modern technology. But the possibility exists. And if it's true, then right now, while you are lying here listening to this story, Eagle is still flying, still circling the moon in silence. No one inside, no power, just an empty metal shell. Its orbit once calculated by the sharpest minds of 1969, still holding precisely in the moon's gravity. The small ship with no one to fly it, flying alone, forever. And the story of humanity's journey to the moon did not end in 1972. April 1st, 2026, more than 56 years after Apollo 11, NASA launched Artemis II from Launch Pad 39B at Kennedy Space Center, Florida. The same pad, the same ground, but 4 different people inside an entirely new spacecraft. The crew: Reed Wiseman as commander, Victor Glover, the first black astronaut assigned to a lunar mission, Christina Cook, who holds the record for the longest single spaceflight by a woman, and Jeremy Hansen, the first Canadian to travel to deep space. On April 2nd, the translunar injection burn fired for 5 minutes and 55 seconds, pushing 4 humans out of Earth's orbit and toward the moon for the first time since 1972. On April 6th, at 1:56 p.m. Eastern Daylight Time, the Orion spacecraft reached a distance of 248,655 miles from Earth, breaking the record for the farthest any human being had ever travelled, a record previously held by Apollo 13 in 1970. Not Apollo 11, not Armstrong or Aldrin, but Apollo 13, the mission that nearly ended in disaster, which flew an unplanned arc around the far side of the moon on its way home, and in doing so accidentally flew farther than anyone else ever had. History is sometimes written by the moments no one planned. On April 10, 2026, the Orion spacecraft, named Integrity by its crew, splashed down in the Pacific Ocean off the coast of San Diego, completing a 10-day journey. All 4 astronauts returned safely. Artemis 3 will not land on the moon. It will test integrated operations in low Earth orbit between Orion and commercial lunar landers from SpaceX and Blue Origin. Artemis 4 will be the first crewed lunar landing since Apollo 17 in 1972. The road back to the moon is continuing, slower than hoped, more complicated than expected, but continuing. There is something strange about this story, not the events, not the technical numbers, not Nixon's speech or Lunar 15 or Collins's 18 contingency plans, but that very small moment, one man in the dark, reaching into his pocket, pulling out the most ordinary thing he could find. There was nothing grand about that moment. Aldrin didn't know whether the pen would hold. He didn't know whether the circuit would stay closed through all 435 seconds of engine burn. He only knew that it was the one thing he had, and not using it was worse than using it. So he used it. And perhaps that is what the universe, with all its incomprehensible vastness, all the distances that make human beings seem almost meaninglessly small, is saying to us in a very quiet way. That the most important moments in a life never look the way they do in films. They look like a person lying in the dark, without the right tools, without enough time, without certainty about anything, but still reaching into a pocket, finding something, anything, and trying. You know, tonight, wherever you are lying, whether something heavy is sitting in your mind or not, perhaps there is no need for a perfect solution tonight, just whatever is in your pocket. Sometimes that alone is enough to keep things going. Thank you for being here and listening to this story all the way to the end. If this video meant something to you, subscribe to Space Lull so you don't miss what comes next. And if you know someone else having a hard time sleeping tonight, perhaps they would want to hear this too.